On November 2nd, 2017, 3 independent teams of physicists from Nagoya University in Japan, KEK High Energy Accelerator Research Organization, and CEA Paris-Saclay in France published a paper in the journal Nature. Using Muon tomography, they fired cosmic ray particles through 2.6 million cubic meters of limestone and found hidden chambers inside the Great Pyramid of Giza, a void the size of a commercial airliner sealed above the Grand Gallery of the only surviving wonder of the ancient world. The statistical confidence was 13.7 sigma. In particle physics, 5 sigma is considered a confirmed discovery. This was nearly triple that. Egypt's most powerful archaeologist, Zahi Hawass, read the paper and went on the record the same day. "They found nothing," he told the New York Times. "This paper offers nothing to Egyptology." 0. 6 years later, on March 2nd, 2023, Hawass stood at the base of that same pyramid on the Giza Plateau near Cairo, Egypt, and called the follow-up discovery the most important discovery of the 21st century. He told NBC News he now believes the true burial chamber of Pharaoh Khufu is hidden beneath a 9-meter corridor that no human being had entered for 4,500 years. Something changed his mind. And what changed his mind changes everything. We thought we knew about the only surviving wonder of the ancient world. We are going to walk through every scan, every detector, and every political battle that stands between modern science and whatever is sealed inside the Great Pyramid. There are 4 chapters to this story, and by the end of the last one, we will know exactly why the most famous building on Earth is still, after 4,500 years, mostly unexplored. The Great Pyramid of Khufu stands 138.5 meters tall today, down from its original 146.6 meters. Its base measures 230.4 meters on each side. The total volume is roughly 2.6 million cubic meters of limestone and granite. And the total volume of every known chamber, every corridor, every shaft that has been mapped in 4,500 years of exploration adds up to less than 1/10 of 1%. The King's Chamber, the Queen's Chamber, the Grand Gallery, the Subterranean Chamber, a handful of shafts and passages. That is all we have confirmed. More than 99% of the interior remains completely uncharacterized. The first person to try to change that with modern physics was Luis Walter Alvarez, a Nobel Prize-winning physicist from the University of California, Berkeley. In 1966, Alvarez launched the Joint Pyramid Project and placed 2 massive spark chambers, each one 0.8 square meters, inside the Belzoni chamber at the base of the second pyramid, the Pyramid of Khafra. His idea was simple. Cosmic ray muons rain down on the Earth at a rate of roughly 10,000 particles per square meter per minute. When they pass through solid rock, some of them are absorbed. When they pass through empty space, more of them make it through. So if you place a detector underneath a pyramid and count the muons arriving from every angle, any hidden chamber will show up as a bright spot, a place where more muons arrived than expected. By 1969, Alvarez reported that he had surveyed roughly 19% of Khafra's pyramid and found no hidden chambers. The experiment was a technical success, but an archaeological dead end. The technology was too limited, the coverage was too narrow, and the political will to continue evaporated. Others tried different approaches. In 1986, an EDF Foundation team led by Mark Alboui conducted a microgravimetric survey of the Great Pyramid, measuring tiny variations in gravitational pull to map density differences in the stone. They found a 30 microgal gravity anomaly in the corridor leading to the Queen's Chamber. 3 boreholes were drilled. All they found was quartz sand at 3 meters depth. Then in 1993, German robotics engineer Rudolf Gantenbrink sent a small tracked robot called Upuaut up the southern shaft of the Queen's chamber. At 63.6 meters from the chamber, the robot reached a sealed limestone block fitted with 2 copper pins. Nobody could explain why a shaft too small for a human being to enter would be sealed with such precision. In 2011, a follow-up robot called Jedi, built by Rob Richardson at the University of Leeds, drilled through that block with a fiber optic camera and found red ochre hieratic numerals on the back face. Italian epigrapher Luca Miatello decoded them as 121, totaling 121 cubits, possibly the intended length of the shaft itself. Every attempt to scan the Great Pyramid had produced fragments and hints, anomalies that led to sand, sealed shafts, and dead ends. Nobody had ever produced a complete picture of what was inside. That changed on October 25th, 2015. On October 25th, 2015, Egypt's Ministry of Antiquities formally launched a new mission called ScanPyramids. It was co-directed by Mehdi Tayyoubi, president of the Heritage Innovation Preservation Institute in Paris, and Hani Halal, professor of engineering at Cairo University and former Egyptian Minister of Higher Education. Halal set the tone at the launch event. He said, "We are physicists and engineers, not archaeologists. Our goal is to use techniques to get concrete results. Then the Egyptologists will interpret them." What made ScanPyramids different from Alvarez was not just better technology, it was redundancy. 3 completely independent Muon detector systems, built by 3 separate institutions using 3 different physical principles, were deployed simultaneously inside and around the Great Pyramid. The first was nuclear emulsion film from Nagoya University, led by Professor Kunihiro Morishima. These are passive detectors. No electronics, no power supply. Stacks of photographic plates coated with silver bromide crystals are placed inside the pyramid and left for months. When a muon passes through, it leaves a microscopic track in the emulsion, a trail of blackened silver grains. After months of exposure, the plates are shipped back to Nagoya and developed, frame by frame, under microscopes. The angular resolution is extraordinary, down to the micron level, but the data only arrives months after the exposure ends. The second system came from KEK in Tsukuba, Japan, led by Fumihiko Takasaki and Hirofumi Fuji. These are scintillator hodoscopes, active detectors made of plastic bars that flash with light when a muon passes through. Each bar is coupled to a wavelength shifting optical fiber, and the grid of bars maps the muon's trajectory in real time. Less precise than emulsion, but instant. The third system was built by Sebastian Procureur and David Atty at CEA Paris-Saclay. Their micromegas gas detectors are the most portable of the 3. 50-centimeter square resistive plates filled with gas, powered by batteries and solar panels, drawing just 30 watts. They were the only detectors that could be placed outside the pyramid, on the north face, looking inward. And that external placement turned out to be critical. In December 2015, Morishima's team placed their first emulsion films inside the Queen's chamber. Months later, when the plates were developed, the tracks revealed something no one had predicted. A region above the Grand Gallery where far too many muons were arriving. A void, a large one, at least 30 meters long, with a cross-section comparable to the Grand Gallery itself, which is 47 meters long and 8.6 meters tall. The KEK scintillator hodoscopes, placed in the same chamber, detected the same anomaly independently. And then Procureur's CEA micromegas telescopes, positioned outside the pyramid on the north face, confirmed it from a completely different angle. 3 detectors, 3 institutions, 3 countries, 3 different physical principles. all pointing at the same empty space sealed inside 4,500 years of solid rock. On November 2nd, 2017, the results were published in Nature. Morishima, Kuno, Nishio, and colleagues titled the paper "Discovery of a Big Void in Khufu's Pyramid by Observation of Cosmic Ray Muons." The statistical significance of the primary detection from the Nagoya emulsion plates was 13.7 sigma. Lee Thompson of the University of Sheffield told Science magazine that the cross-validation across 3 independent detector systems made the finding very robust. Christopher Morris at Los Alamos called it pretty amazing. And then Hawass said 0. But the ScanPyramids team did not stop. Between 2018 and 2019, they deployed additional Micromegas telescopes inside the Grand Gallery and the unfinished subterranean chamber. The new data refined the void's minimum length upward from 30 meters to 40 meters in a single continuous segment. The slope of the void remained uncertain, but its existence was no longer debatable by any scientific standard. If you are watching this and finding it as extraordinary as we do, a like and subscribe helps us bring more stories like this one to light. It takes 1 second, and it tells the algorithm that this kind of research-driven documentary matters. Meanwhile, the team had a second anomaly to investigate. As early as October 2016, Nagoya's emulsion films placed in the descending corridor had detected a muon excess behind the Chevron Blocks on the pyramid's north face. These Chevron Blocks are massive limestone slabs arranged in an inverted V pattern above the original entrance to the descending corridor. Sir William Flinders Petrie measured them in 1881 at a mean angle of 50 degrees and 28 minutes. They are a load-bearing structure designed to distribute the weight of the stone above. But nobody knew if anything existed behind them. Between 2017 and 2022, the team converged on the anomaly with everything they had. Additional emulsion films in the descending corridor and Al-Mamun's tunnel. CEA Micromegas telescopes positioned directly in front of the chevrons. And starting in 2020, a new partner joined the project. Christian Gross and his team at the Technical University of Munich brought ground-penetrating radar and ultrasonic testing equipment that could measure the structure of the stone from the surface. The result was published on March 2, 2023, in Nature Communications. Procureur Morishima and colleagues titled it "Precise Characterization of a Corridor-Shaped Structure in Khufu's Pyramid by Observation of Cosmic Ray Muons." The corridor measures 9.06 meters long, plus or minus 7 centimeters. Its cross-section is 2.02 by 2.18 meters. It sits behind the Chevron Blocks, running roughly horizontally into the body of the pyramid. And then came the moment that changed everything. The scientific committee, chaired by Zahi Hawass himself, authorized a direct look. Christian Gross's team used high-frequency ground-penetrating radar to locate an existing joint between 2 of the Chevron Blocks. The gap was 5 millimeters wide. The team had a purpose-built endoscope manufactured to fit through that gap. 5 millimeters in diameter, thinner than a pencil. On March 2, 2023, at a press conference held at the base of the Great Pyramid, they showed the world what the camera had recorded. A roughly hewn limestone corridor with a gabled chevron ceiling continuing backward into the pyramid. An irregular floor with no soot, no footprints, and no artifacts of any kind. Just raw stone that no human being had seen since the builders of the Fourth Dynasty sealed it more than 4,500 years ago. This was the moment Hawass reversed himself. He called it a major discovery. He told NBC News it was the most important discovery of the 21st century. And then he made a claim that went far beyond what the physicists were willing to say. He stated that in his opinion, the true burial chamber of Pharaoh Khufu lies beneath this corridor. The ScanPyramids physicists refused to endorse that reading. Sébastien Procureur explicitly pushed back against media reports that the team was close to a burial chamber. Procureur has always described Muon tomography with a specific metaphor. Muons, he says, are like marathon runners. They do not all start with the same energy. Depending on the difficulty and length of the race, a number will stop along the way, and only a fraction of them will cross the finish line. That fraction tells us about the difficulty of the race. It does not tell us what is waiting at the end. So what could the void and the corridor actually be? Three competing hypotheses exist, and none of them has been falsified. The first comes from French architect Jean-Pierre Houdin, who has argued since 1999 that the Great Pyramid was built using an internal ramp that spirals upward through the structure. In Houdin's model, the Big Void is a remnant of that ramp, a second grand gallery used as a counterweight passage during construction. This challenges competing theories that propose external ramps, or as debunked by modern archaeology, alien construction methods. Houdin updated this interpretation in his 2022 memoir and in an October 2024 self-published paper that reintroduced a little-known third anomaly, a cavity on the northeast edge of the pyramid at roughly 110 meters elevation that the ScanPyramids telescopes detected in 2016, but never published at full statistical confidence. The second hypothesis comes from Giulio Magli at the Politecnico di Milano. In November 2017, Magli argued that the void could be a pyramid texts chamber, housing a ritual iron throne made of meteoritic iron, oriented toward the northern stars. This reading is highly speculative and has not been endorsed by any member of the ScanPyramids team. The third interpretation is structural. David Ian Lightbody proposed in 2018 that what the detectors read as one continuous void may in fact be two construction space zones flanking the Grand Gallery, gaps left intentionally to reduce the structural load on the gallery's corbelled ceiling. The problem is that Muon tomography can detect where stone is missing. It cannot tell you why, and the history of accessing hidden spaces inside the Great Pyramid is not encouraging. In 1837, Colonel Richard William Howard Vyse, a British Army officer with more ambition than patience, used gunpowder to blast his way upward from Davison's chamber, the one stress-relieving cavity above the King's chamber that had been known since 1765. Over the course of several months, Vyse's explosions opened 4 more chambers stacked above Davison's, each separated by massive granite beams. In the uppermost chamber, which Vyse named Campbell's Chamber after the British Consul General, his team found red ochre quarry marks, including the cartouche of Pharaoh Khufu, written in hieratic script by the work gangs who built the pyramid during the Old Kingdom of Egypt. This remains the only direct epigraphic evidence that the Great Pyramid belongs to Khufu, and it was found by blowing holes through 4,500-year-old granite. That kind of access is no longer acceptable. Egypt's Antiquities Protection Law, Law No. 117 of 1983, as amended in 2010, 2018, and 2020, classifies every Egyptian antiquity as state property and places all excavation and research authorization under the Supreme Council of Antiquities. Unauthorized access to archaeological sites carries penalties of up to 1 month in prison and fines of 100,000 Egyptian pounds under the 2020 amendments. Damaging immovable antiquities can carry sentences of up to 7 years, and with tourism contributing a record $16.7 billion to Egypt's economy in the most recent fiscal year, the political calculus around any invasive investigation of the pyramids is not purely scientific. The ScanPyramids mission operates under a strict non-invasive mandate. No drilling has been authorized. No physical access to the Big Void has been attempted. The only reason the endoscope could enter the north face corridor was that it fit through a pre-existing 5-millimeter joint between the Chevron Blocks, a gap that was already there. There is one project that could break the stalemate: the Exploring the Great Pyramid Mission, led by Alan Bross at Fermilab, with archaeologist Mark Lehner from the Institute for the Study of Ancient Cultures at the University of Chicago and physicist Ralph Ehrlich at the University of Virginia, proposes a fundamentally different approach. Instead of small detectors placed inside or near the pyramid, the EGP mission plans to surround the entire base with very large scintillator bar telescopes housed in shipping containers, totaling roughly 1,300 square meters of detector area. Their February 2022 preprint on ARXIV claims the system would deliver upwards of 100 times the sensitivity of ScanPyramids and produce the first true three-dimensional tomographic image of the pyramid's interior by collecting an estimated 100 trillion muons over a 3-year imaging run. The Egyptian Ministry of Antiquities granted approval in early 2018. Fermilab and the University of Chicago's Big Ideas Generator provided seed funding. We started this story with a physicist's paper and an archaeologist's rejection. 6 years later, the archaeologist reversed himself, but the physicists still refuse to speculate. The void is real. The corridor is real. The endoscope footage is real. 3 independent detector systems, confirmed at 13.7 sigma, cross-validated by ground-penetrating radar, ultrasonic testing, and electrical resistivity tomography in 2025, have placed a sealed 40-meter chamber and a sealed 9-meter corridor into the peer-reviewed record. And yet more than 99% of the Great Pyramid remains a question mark. Hawass told the world the answer is down there. Procureur says the data cannot say what the answer is, only where to look. Houdin says the answer is about how the pyramid was built, not who was buried inside. And somewhere behind, 2.6 million cubic meters of limestone, a space that has not been touched since the age of the pharaohs, is waiting for the first detector sensitive enough to see it clearly. The only question left is whether we will be allowed to look.